Unreal Header Tool, or UHT. What is UHT? If you've been programming in Unreal for a while, you've probably seen UHT or Unreal Header Tool mentioned. Unreal Header Tool is a tool that first reads your header files, or your .h files, and then second, UHT generates files based off what it reads in those header files. And it adds features to effectively the C++ language. So here we have this UPROPERTY system that prevents these from being garbage collected. And we have regular C++ variables that do not have UPROPERTY, that are not part of the garbage collection system, but these are features that have been added. We have UFUNCTIONs, which allow functions to be called from Blueprint scripts. We have things like make them pure, which changes how they look in scripts. We have BlueprintImplementableEvent, which is just an event that happens on Blueprint side. We have BlueprintNativeEvents, which have native callbacks. All of this is features added. We have things like RPCs that execute on the client, or it executes on the server, or it executes everywhere. And these functions get mapped to these underscore implementation functions. And it all seems rather automatic and magical if you're just writing the code. But if you drop a breakpoint here, you can see that there's a lot going on here. So something has worked its magic here to make this work. And it also adds features like an onRep callback for when this variable replicates down from a server. In the CPP file, we do a little bit of setup, but we're not ever actually doing the setup for this onRep. Like, that's not mentioned down here at all in this lifetime property setup. This is just marking the property dirty so it knows to replicate, and this is just setting up some properties about this replicating using the push model. Also, there's this cheat display all where you type the name of the class and then a property name, and you get these debug views of what the property currently is. And all that we've done here is just add a property that is set to 2 by default. UHT also adds new compile errors that guide you. So in this case of setting an RPC, it needs to know that a reliable or unreliable RPC, and we forgot to do that here. And so it generates a compile error here, letting us know what we need to do to fix this and make it work correctly. So why look deeper into UHT when these files are generated? You're not really supposed to have to worry about them. Sometimes you can have natural compile errors show up in the generated code. So here's 2 cases where I have ZConstruct showing up as compilers in this .gen file. And this is actually user error on my end, but I'm seeing the error first in this .gen.cpp file rather than my code. And so sometimes these generated functions also show up in call stacks. And just having an understanding of a high level what's happening, what's being generated, can really help you diagnose these. In this case, I just need to link a module. I mean, you can see my videos on Niagara and Metasound for that, but it's a really trivial fix. Knowing a little bit behind what's being generated helps you diagnose this and solve it. So the first time you write a UCLASS, you've probably noticed some things. You have to prefix it with UCLASS and denote some properties here. You have this generated body thing. Your properties have this UPROPERTY macro. Your functions have this UFUNCTION macro. And if you're curious to see what these macros evaluate to, and you start following the definition, you'll be surprised in that you'll find they don't really evaluate to anything. So if we follow generated body, we see it's defined here as this macro combine current file ID, line number, and this generated body thing. But if you start searching for these, you just don't find them. And then the same thing for UPROPERTY and UFUNCTION. If you go to the definition of UPROPERTY or UFUNCTION, you'll find that they're not really defined. But you will find this text above it saying parsed by Unreal Header Tool. There's also another curious thing. If you forget to include this .generated.h file in your header file, you'll get a compile error. And so in this case, I have this header file here. There's the same name with a .generated.h. And if I forget to include this, you get the given include must appear at the top of the header, following all other includes, include this. So it tells you what to do. And so this is rather explicit that there's some generated files happening as part of Unreal Header Tool. So what files are at play? We have the standard header file that you write, and we have a CPP file that you write. But the UHT process will generate this .generated.h, which is a header file that is included up here. And then it'll also generate a file.gen.cpp, which is its own translation unit, which provides bodies to some of the functions injected from this file. So if we were to take a look into these files, you can see how this starts to work. We have the generated body here, which defines these macros, which adds functions that just get populated right there. And I'll go a little bit more into detail about that a little bit later. But we also have the property here, and so there's things here related to this property. And then we have the function, which also has things related to this function in the .gen file and the .generated. And so these things show up in different places. The generated body is in this file.generated.h. The property stuff mostly shows up in the file.gen.cpp. the ufunction stuff shows up in both the generated.h and the file.gen.cpp. So where can you find these files? Well, my project is UVCPP tutorials. Nested in there is an intermediate folder. The intermediate folder is like a temporary folder. You don't generally check that in because this stuff is just generated code that gets changed and you don't really want to bother tracking all of that in Git or Perforce. But if we go into this folder and follow this path, you'll see that there's all these .gen.cpp files and .generated.h files. And this is for the project. If we look for plugins, for example, I have a plugin here, test dependency plugin, and there's an intermediate folder in that plugins folder structure, and you can drill down into that to get to UHT and find some generated files there. So let's explore regular C++ compilation and then compilation with UHT involved. So this is a rough approximation of what happens. There might be a few mistakes here, but you can roughly assume this is how it works. So in regular C++, we have a set of files, a header file and a CPP file. So I have a file called A, a file called B, a file called C, and there's a header and CPP file for each of those. First, we run the preprocessor, which effectively copy-pastes the header file into the CPP files. And we're really only left with the CPP files. These are the translation units and are what are actually going to get compiled. The header files are effectively copy and pasted into the top of these. You can see here where I have some fake includes. This one includes all three, and we see that it got all three headers copy pasted into this one translation unit. After that, we run a compiler, which changes it from this form into these .asm forms, which is assembly language. Then we have the assembler, which converts the assembly instructions into binary. Then we have the linker run, which links all these translation units together and allows them to call functions amongst each other. That's a really rough summary of how C++ compiles and works. But if we consider it with UHT and how that works, we start out with the same set of files. We have this header file, CPP file. We run UHT, which then generates .generated.h files and .gen.cpp files. So from these 6 files, we now have 12 files. And then we run the preprocessor again, same step. And that preprocessor copy and paste all the h files into their .cpp files that are needed. And we get this sort of intermediate form. And then we run the compiler, which builds our assembly files again. And then we run the assembler to get binary files. And then we run the linker to link all the binary files again. And I tried to show the picture here. In a normal case, we would have had 3 files kind of linked together here. But now we still have those 3 files, but these kind of adjacent .gen.cpp files that are also compiled, which came from UHT. And so that at a high level is how it works, at least from my understanding. There's some additional files, like a timestamp file in this classes.file and a net.gen.cpp file, but we'll get to those later. Now there's a few things to understand before we dig into these generated files, but just to give you a quick preview, this is what the .generated.h file looks like. A lot of macros in here. And I've went through and labeled what these things are roughly doing, at least as far as I can figure that out, but we'll explore that later. This is roughly what a .gen.cpp file looks like, so this is something actually sent to the compiler to compile. And I've labeled those also, and again, we'll get into that in a moment. But before we analyze the generated files, things will make a lot more sense if we understand some concepts first. So let's review some things. Reflection is a language feature provided by some languages. So here I have an example of C# and Java. And what reflection lets you do is kind of like looking in a mirror of a type. It lets you change things about a type without really knowing things about the type at compile time. In some ways, it lets you change things about classes by introspecting it. So if we look at the C# example, it'll make more sense. I have a class here and it just has a float property and it has a function. And we don't actually call these directly. Instead, I have this main method testing it, and it uses reflection to manipulate the object. So instead of using the object, we say get the type from the object, and that's the reflected type. Reflected type, we're able to get the property with this string name, myFloat, which is able to find this thing. And then we're able to read the value if we pass in the object to read the value from. And we get the value, and we cast that to a float, and then we can read the float, and we see down here that the value is 5 is printed, which is what we had set. We can also set the value on the object to a value of 10. We see down here, it printed. I was able to read it. And I did a cast to the object to read it directly in this case. So this was a direct read, just to make sure that changing it this way actually propagates to the object. And then lastly, we can do the same thing for functions. We can request a function, myFunction, which is right here. And that internally prints out and then returns a number plus 2. And we invoke that function on the object, and we give it some parameters of 5. And then I'm able to see a result, which is an int, those matched here. I casted it to an int, and then print the result, and we can see it actually printed 7. So it took that 5, added 2 to it, and printed 7. And this is all like an indirect way of calling functions and methods. And then here's a Java example. It does the same thing. It's slightly different names. So we have get declared field for my float, and we have like getting the value on the base object like that, but it's all effectively the same. We can set the value here, use a reflected field, set on object the value, and we print it out. And same thing for get declared method of that name, invoke it on the base object with a parameter of 5, cast a return value to int, and then I print out the int, and we get all these same values. So this is C# version and Java's version. But using things like I just showed you isn't really the power of reflection. Instead, reflection allows you to do really cool things like create generic property windows in like a gameplay debugger or some sort of tool. And so here's some pseudocode C# that effectively gets an object that it knows nothing about. It gets the type, gets the properties, iterates over the properties, and then we can print out stuff about the properties. And we could, in theory, use this to write to properties. So you could build like a property window that just says, oh, there's a float, let me type a thing in, and it'll pass that value into the object without ever having to write specific code that says, oh, let me change the thing called myFloat. It's just able to reflect and then expose it. So that's really more of where this would be useful. You can see here it printed out. This type has a property float of single, which is, half of a double effectively. So same thing as just float, and it has a value of 10, or at least 10 currently. And so that's really where reflection's power comes in. But reflection is missing from C++, and it's been missing for a long time. There are some proposals to add reflection. Looks like currently C++ 26, but there isn't reflection by default in C++ like there is C# or Java. However, a lot of people have built reflection systems. So if you search for C++ reflection under the language C++, you will see lots of repos that appear to have built their own version of reflection. The point is that lots of people build reflection systems to add it to the language. And Unreal is no exception. Unreal has built its own reflection system. So why am I talking about reflection? A lot of the generated code is around building a reflection system in a large part. And so understanding reflection kind of informs you what's being built and gives you some understanding of what you're seeing. And so the first thing is for UClasses. So here's UClass. There are two related things. So if you look into the code, you'll find that there's this function called getClass. There's also a static class, and they return this UClass pointer. So this is its own type, and this UClass effectively seems to represent the reflected properties for a given class. And so the getClass gives you the most derived thing. So if a blueprint is inheriting this type, this will give you the blueprint, as you can see there. The static class gives you specifically the thing associated with that type. So ignoring whatever the current object is, just get the static reflected class here. But generally, you probably want the getClass method to give you the derived most class. And so you can see here, I have this class and I have various properties. I have functions on it. And here we can ask the class, the UClass, to find a property by its name. And I just have a string for this name, myFloat property, which is right here. And same thing for my blueprint callable, find function by name. This is the name. You can see my blueprint callable function is right there. And it's able to return these reflected types like f property or u function. And just so you know, you don't have to type a string every time. There is a macro to help you do this type of thing called get member name checked, which is kind of a compile time check to make sure it actually exists, that property on this type. And same thing for function. Get function name checked and get member name checked. And so we have this ability to kind of request a UClass to get reflected data about a given class. So you can see how this is starting to resemble the C# and Java that we looked at. And this is actually extremely useful for other things that actually are gameplay. So for example, if you wanted to spawn an actor in the world spawn actor, say we want to duplicate, we can get the derived most class like this, get class, and we can spawn another one somewhere in the world using the world spawn actor. And so this is able to take this UClass, the reflected class, and somehow translate and instantiate this C++ class. And so this thing is a blueprint class. So we're able to do this without ever writing code that exposes this blueprint type to C++. So this is a really powerful feature. It's perhaps a little subtle in understanding it. And then there's other features that are useful from this reflected thing. So you can get this superclass, which can be used in various ways. You can get the interfaces for that given class to iterate and see if it has an interface. There's better ways to check that, but perhaps there's a different use you have here. And the more you look at this, you start to see that it's pretty widespread, the use of reflection in the engine. For example, here I have a data asset, and this data asset spawns an actor class. And you've probably seen T subclass of. and you specify the type, and then in the editor, you pick the blueprint subclass you want. And then in the world, we can pass that T subclass of to spawn actor, and it's able to do it just like we did with the other one with UCLASS. And the reason this seems to work, if you look deeper into it, under the hood, it's the same thing as just providing a UCLASS. T subclass of has a property called class, which is of type UCLASS. And so this is some examples of reflection being used in regular gameplay as far as the engine is concerned. Since we're on the topic of UCLASS, I feel like it's worth mentioning the class default object, or CDO. CDO is effectively like a singleton that has all the default values on it. So there's a couple ways to get defaults. The thing you should look at is getting the UClass. So here we have get class, the derived UClass, and then on the UClass, you ask it for the default object of that type, and it gives you back a casted version of that default object. And that default object can be used to restore state. So in this case, I have a float property, default is 5. On this level instance, I've set it to 123. And here I have a function called readCDO that effectively wants to restore it at runtime. So what it does is it requests the CDO, and then it reads the CDO's version of this, which is going to be 5, and it puts that 5 into the instances variable here, and then I log it, and we can see down here it changed from 123 to 5. So that's what a CDO is. It's effectively like a singleton object that has the default values. And there is another get default, which is this here, and this is more typed to this specific class. It won't give you the blueprint class default object. You can see the names here. This is the blueprint reflection tester, and this one is the default UHT my reflection tests. And if you look at these functions, you can see why there's two get defaults. One of them provides a class, the one that gives you the static class effectively, or this right here, the one that gives you the default that is this type and not the derived type. That one uses the static class, and that's why not the current class. This other one that takes a UClass just calls the class get default object. And so that's why there's a difference. Be aware of that when trying to get a CDO, that make sure you call the right function for what you need. And so in that C# and Java code, we saw us writing values back to properties and calling functions. So here's some examples from code that do that. Here we have a function invoked by reflection and a property set in Blueprint. So there's this function here defined in gen.cpp, and ultimately it's calling our function that we wrote in our.cpp file. Here's the call stack. There's a lot of processing happening here, but you can see that the function itself does this like building a struct, putting the parameters on the struct, get the function, like reflected function, pass this parameter struct, and then it reads the return value from the param struct as like an out value. And all we did in the header was define this .h thing, and we wrote this right here. And the parameter struct here is this. It just has the value, the return value, and that's what we passed to the system, which is able to take this and execute our native code and put this 5 in that struct. So this is all generated, but this is how reflection works to invoke a function. And the same thing with the blueprint setting a property. There's this container pointer to value pointer. You give it a reflected property and ultimately convert that into a pointer that you can write to. Seeing those and looking up things online, this is what those C# and Java examples would look like. We have a type here that says myFloat and a function to call. The function just takes the value passed in and adds 2 to it. And we do the same thing. We get the UClass, the derived type, get the reflected property by finding property by name myFloat, which is right here. And then we convert the object's address into effectively a float pointer address. So we say the float property, convert the object address into an address we can write to, and I'm able to read the old value here by dereferencing the pointer, and then I try and write 10 to the pointer, and then I just do a hard cast to the type to double check that the float actually changed. And if we look at the execution, it started out as 5, which is logged right there, and then it was logged that it was changed to 10, which we did there, and we logged here. And so this is not really kind of how you would use reflection, but I wanted to show it as an example. And the same is true for this U function. You can ask it for find function by name, get my function, which is right here, or defined here in the header. And then we set up that struct parameter thing I was showing you ourselves. So we have one parameter, we have a last value in the struct, which will act as a return value, it seems. This is a little implicit. I'm not sure, maybe this shouldn't be done in actual code, only generated code. But nevertheless, it seems to work. So I set up this parameters. I set my parameter x to 5, like we did in the other examples. And then I do a little bit of validation to make sure it's the same. This is really low level, but we say that ensure effectively, we're going to ensure that this is a valid struct parameter for this function. So num_params is 2, so ensure that it's 2 for this function. Ensure that the param size matches the struct size, so the size of the struct. And ensure that the offset of the return value, or what I think is going to be return value, is actually the return value offset. And then if all that's true, ensure that it's true, Then we do that process event, which takes in the function and the parameters so that we can invoke that event via reflection. And then I'm able to read the return from the return value in those parameters. And logging shows that that worked. Again, I would not recommend this, but I just wanted to show the example. So we saw that UCLASS has an associated UCLASS pointer. But what about these types? So we have USTRUCT, UENUM, and UINTERFACE. Well, if we look at a USTRUCT, here I have one defined. We've got a USTRUCT, generate body, and then we have some properties set on it. We have various ones. We have a myStruct property, which is a float, another float property, an object property, a TObject pointer property, and a array property. And we can do something like get UCLASS, but it's the static struct for this struct. And it returns this script struct pointer, which is effectively a reflected type for this. And we can use this reflected type to find properties. So we can say get name checked, and we can find property by name and do reflection stuff there. The same is true for enum. So here's an enum that has two values, first value, second value. And there's this static enum function we can call to get an enum pointer, UENUM pointer, which seems to be a reflected enum. We can do things like get the name. We can get the index of the value by name. So that's a second value. We get a name by index. And we can log those, and all that is expected. This is effectively an enum that has been reflected. And UINTERFACE, we have this UINTERFACE type, and then we have the type you actually inherit from. You can see my video on interfaces about that. And that just seems to use UCLASS. There's not a specific one here. So you can get the static class of that UCLASS and do some reflection here by finding function by name, event name, similar to what we've seen. And so the reflection system and the engine seems to rely on these like reflected types. So there's like UCLASS, UScriptStruct, and UENUM. And there's a lot more. So all of those inherit from public UFilled. And you can see all the different types of reflection types in the engine. And just to make that clear, a lot of these are inheriting from public UFilled. So we have UCLASS and UScriptStruct, which are both UStructs. And the UStruct is a UFilled. And UENUM is its own thing. It's just an inherited from UFilled. All right, now that we've seen what reflection is, how it's used, how it can be used, what it can do, we can now start going into the generated code. And so I just want to give a disclaimer that this is generated code. You're not really supposed to be modifying this stuff. You let it generate. I would not worry about memorizing this, but just seeing what it does at a high level seems to be useful. But this may change from version to version. So each engine version might update this because this is not really code you're meant to be directly calling, but it's just code to enable the features that you're used to when writing C++ and Unreal. But this is just what I found from digging into the generated files in UE 5.4. It may be different in yours. So there's a pattern that emerges. First, we'll look at UCLASS. There's this ZConstruct pattern. What it seems to be is effectively constructing a reflected class. So it lazily evaluates, do we have this outer singleton thing in our registration info? If we don't, that's not symbol, then it constructs a UCLASS. And this is what builds the UCLASS that we can use to read properties and do reflection on. This function here. Here's the call stack of when it gets done in the engine. This is a very early startup thing with loading modules and stuff. But you can see here, here's the construct UCLASS. Go down to here, you can see a new UCLASS is created, and there's a no class register func. And if you trace that all the way down, so no class register func, which is in declare class, I believe. And then there's a static class function, get private static class. Keep going. Eventually you find that we allocate a U object and we use a like placement new. And then as this progresses, we use some class params to effectively build the U class, the return class. And the same thing is true for UStructs and UScriptStructs. So we have the ZConstruct pattern. If it doesn't have one already, it calls this construct UScriptStruct, and here's the call stack for when it does that. And that's going to return us this UScriptStruct. We can see it does a new operator, and it builds a new struct, and then eventually we set all the properties and whatnot. And so that seems to be how that reflection data is built. Similar thing with UENUM, there's a ZConstruct. If it's not populated, then it calls construct enum. And this is the call stack when that happens during engine startup. And this is what it looks like. Eventually it calls this construct enum and it does a new operator. We get this new UENUM and it does some reflection stuff, iterating over properties and assigning their names and or something like that. So you can see here it does some work using the reflected data to effectively build this UENUM. UINTERFACE has a similar pattern, ZConstruct, but this one's really doing the same old construct UCLASS. Here's the call stack, but it's effectively the same as UCLASS. Now, to understand what we see in the files, there's a few C++ nuances to go over. I'll go over this quickly in case you're not normally programming in C++, but don't consider it a tutorial notes. You can look up more information if needed. But first is class or struct member statics. So like other languages, there's the concept of member statics. So these are kind of shared. You have a static function and you can have a static variable. The static variable is shared, and you can just have regular variables. In C++, you have header files and you have CPP files. For the functions, you define the body in a CPP file. So this is how you set up a static function, declaration, and then over here is where it's defined. And what's slightly confusing is that in C++, even though we define the static variable here, we still also have to set up a definition here. So we've declared it here, and we've defined it here. So that's where the default property goes. And just to show you the static variables, how they work, we can call a static function. There's no object instance here. We can print out a static variable. There's, again, no object instance here. We can create two object instances. We can change the static variable, and then I'll print the other instance version of that static variable, and we can see that that value gets changed. So by default, it's 100, and here on this alpha object, I set it to 7, and then I print beta, the beta object, and it's 7. So it was a shared variable. On the alpha one, if I change a member variable to 8, which is by default 0, then print the beta version, the beta is 0. And so that's the difference between member variables and static variables. Additionally, in C++, you don't even have to define the type in the header. The struct or class can be defined in the CPP file up here. So we're declaring the two static variables. So here it has declared two static variables, but we still have to define them. And so you'll see this pattern a lot in the generated files. It declares a struct, then it defines the struct variables below it. And it works the same as before, able to call a static function, read a static variable without an instance, change it for all instances, and member variables work normally. Then there's also function local statics. So here I have a header file with two functions. There's an alpha function and a beta function, and it just counts. And inside of this function, we have a local static to that function. It's a counter. We increment it every time the function is called, and this is saved basically associated with this function. Same thing with this beta function. Has a counter, increments the counter every time it's called, and prints out the current count. And so I have this run test. I call the alpha one 3 times and the beta one 2 times, and we can see the alpha prints 3 times, beta prints up 2 times, and the variable is incrementing each time it's called. Lastly, there are file statics. So it's another type of static in C++. Here I have a header file and a CPP file, and then a different header file and a different CPP file. This is the alpha files, and this is the beta files. And these CPP files just have a global variable inside of them to this file. And you might expect that this would only be associated with this file, but if you try and compile this, you'll get a linker error saying multiply defined. And so this could have been references externally, and so the linker is calling out, like, if you tried to reference these, it wouldn't know which one to do if they were like external variables or something. And so what you can do is put static in front of those, and then suddenly these become kind of scoped to these CPP files. I believe the proper term is internal linkage to this translation unit or this translation unit. And now these can have the same name, but different values. And these variables aren't that special, even though this is static, we can't use it here just implicitly. But what we could do is define this function to get it. So right here, we have a function to get a pointer to this variable. And then I wrote a test over here where we call the function to get a pointer to the static variable, and then we can manipulate it. And ultimately, you can see that the value was able to be changed to 1, 2, 3, 4 using a pointer that we got from a function. And so there's just some nuances with statics in C++. The other nuance is that you can define functions in different CPP files. So this is used also for the .gen.cpp files to provide bodies to functions that were in the .generated.h files. So here we have a class, and it has two functions, a normal function and other file function. This function is defined in another file. So the normal function is defined right here, normal function, in this CPP file. This is multifile class.cpp, and this is multifile class.h. I have an additional CPP file, and here we define the other file function. And then lastly, this is a main method test, and we're able to call both functions normally. There's no issue at all. And this is just a reminder that macros are effectively copy-paste text. So you could have a function that prints a value out 3 times, this argument, or we could define a macro that takes an argument and we print it out 3 times. If you do this, though, you'll see a difference in behavior. The function, if I increment it here before we pass it into it, it prints it 3 times, and it did the increment to 1 before the function was called. However, with a macro, we'll see that if I call this macro and increment it, it counts up each time the macro is printed. And the reason for that is this is effectively copy-paste. So this is going to basically turn into that. So we inject these functions here, and we end up getting 3 increments. And that's why, in general, in C++, it's recommended not to use macros in this way. But macros are still useful for basically copying and pasting functions around. So here I have an example of adding functions to a type based off a macro. There's this enable debug functions defined I've set up here. You can set it to 1 or 0. And if it's defined, then this macro define debug funcs adds this method here that takes a class name and just prints out the type. And in this class down here, I have a regular function. and then I call my macro with the current type. And so this optionally adds functions to a type. And so in main here, I make an object type, call the say hey function, and I say if the debug functions are enabled, call the debug name. And you can see if it's enabled, I see the hello, and I also see this debug func with the type name. If it's disabled, I only get the first thing. So that's how macros can be used to like copy paste functions into types, which is used extensively in these generated files. So again, the files involved here, we have the header file that we write and the CPP file that we write. And then there's the generated header file and then the generated CPP file. If we take a look at the file.generated.h, the generated header file, we can see there are effectively some macros that get defined. And these macros ultimately get pushed into a macro below that is helping with the generated body. So starting from the top, there's some includes here that provide some macros like these. So it includes some things. There's an include guard to catch, apparently, if you forget some things like a pragma once. So it catches it here, which probably stops some compile errors. There's this helper macro that defines a class and serializer and some other things. So it friends the ZConstruct struct. And this declare class does a couple things like it defines the super, it defines the ThisClass, the static class function, things like that. And then below that, there is this enhanced constructors thing that declares some constructors. And then there's some macros for more advanced constructors, like one that takes a vtable helper and the default constructor. And there's also a virtual destructor provided. If you're familiar with C++, you'll know that we're getting to do this for a polymorphic type. And so creating some headaches, and so the header tool just does this for you. So it's just not a thing you have to worry about when programming with Unreal types. And then below this, there's this generated body helper macro, and that's pulling in these two. There's a function for getting the static class that's a template override. And then this bottom bit is actually really important. It's undefining a current file ID and then defining the file ID to be this long string. If we look at this a little closer, if we go to a type, you'll notice that we have to include the .generated.h before the type. And so that is what defines this thing here. And if we look at the generated body again, we'll see that it points to in the engine this macro combined current file ID, line number, and underscore generated body. Well, this current file ID is the file ID generated right here at the end of the file. And this undefined is probably why you have to put this at the end, because the ones above this change it potentially. So the last thing included will be the last file ID. And this file ID matches up with that. The underscore is here. Line number is 12. Which you'll see the generated body is at 12. And then we have underscore generated body, which goes here. So that defines this macro for generated body. So that's how generated body uses this macro, which in turn uses more macros up here to add functions to your class. If we look a little bit into that declare class, note I did edit this to make it a little more compact. There's a lot of stuff here, and this is in the object macros header, but there's things like the super. So if you ever saw super : and then have function calling the super, that's where the super gets defined from. That's not part of C++, that's part of the Unreal toolset. And same thing for this class. If you're doing like delegate bindings and that kind of stuff, you often can see this class instead of typing out the class each time. So there's a lot of things here. There's like new operators and delete operators, but some of these are for internal use only. But there's like static class here, static package, static class cast flags, some operators. So a lot of this stuff comes from this declare class, which is used in the .generated header. This declare serializer also adds some serializer stuff for archives, slots. So that covers the .generated.h file. Next is the file.gen.cpp. So this one is the one that contains a lot of stuff. This is a full-fledged CPP file that is compiled. It's harder to read, so I broke it into two panels here. So you can see this and this, and it does look rather cryptic, but there is a underlying pattern here. So at a high level, there's really two major operations that seem to happen as far as I can see. There's the types setup, which defines all this setup stuff for reflected properties. And then there's the type registration, which takes this and shuttles it off to be registered later. And so I've annotated all this, and we'll go through this now. And so at the top, we have these header files that get included. Again, this is including the actor file that we made, some other includes. Then there's this section called Begin Cross-Module References. And we start to see declared ZConstruct functions. And so if I annotated this with a star, we can see the star pop up later. These are just the function declarations. Their bodies get populated later, except for things like this, which is defined in, I guess, the engine's generated file for actor. First thing is this static register natives. which if we look at another file in this box here, we can see as we populate U functions, it builds this out. And so then there's this implement class no auto register, which gives us some stuff like get private static class defines Z register and info, things like that. And then we finally do get a body of this Z construct. So the star associates it up here. So the Z construct no register, which just calls static class. Below that, there's this Z construct UCLASS actor statics. And so this is a struct that uses member statics to hold data. So if you recall the member variable statics for classes and structs, that's effectively how this is working. We have things like this static array that's declared here, and then it gets populated below, like right there. So what it has is some metadata if it's compiled using this compile flag. And that's things like where the active file path is, the module relative path, things like that. Then we have this dependent singletons array, which is an array of function pointers. If we look at how it's populated down here, it's got the Z construct of the parent class, the Z construct of the package, which is the project UECPP tutorials. Then below the dependent singletons, we have this static class type info, which looks like it is some type traits for the current class. And this is available at compile time because it's const expr, so we don't have to provide a body for that one. This is the actual definition rather than a declaration. But lastly, in this statics struct is the class params. This one is very important. The class params is effectively where we store all this reflected data, and we send it off to basically build the U class in the Z construct. So we'll see that in a moment. But if I scroll down here, the class params, when we actually populate it with stuff, there's all this data here, the types. You can see the parameters to this. It's effectively like a register function, properties array, function link array, dependent singleton array. So a lot of things get populated here. And as we add like U functions or U properties, this gets changed. You can see a zoomed out image here that it's adding things for U functions there and adding things there for U properties. We'll get into that in a moment. But then finally, we have this Z construct with our actor. And it's doing that pattern again, where it lazy builds the outer singleton and it calls this construct UClass. Notice we're passing in the class parameters here. And if you were to step through this, you would see that the class parameters that populated up here, so it's used to ultimately build that UClass. So this is how it's building the reflection data. And there's a static class function that we use to get the static class. This is like a templatized version. Then there's some vtable constructors that are defined here rather than declared. See the macro here that is just doing a simple vtable helper constructor. There's our virtual destructors body that was provided in the .generated.h file. And then lastly, we have the begin registration, which has kind of got two phases. The thing above it is what shuttles the like Z construct functions, static class functions, the name, and some other things. And then once that is built into this f class register info, below there's another struct that takes as part of its constructor the class info, which sets it up to be registered. And so you can trace through that a little bit. That's class register compiled in info, has an outer register, inner register. And when debugging that, I found that to be the Z construct function and the inner one to be the static class function. And this gets forwarded to a variadic argument thing, which ultimately registers class info, struct info, and enum info. And all this is engine code rather than generated code, by the way. The generated code is what uses this engine code. And so there is a deferred register. And so registration of the reflection data is deferred. It seems to be called at a later point in engine startup. So while it sets up all this static data, it's not used until later, it seems. And so if we trace through this, we go to what I was showing before, this compiled in info, variadic arguments, where we have the classes, structs, and enums defined. It does register here. It's register compiled in info. And ultimately, this is going to call this thing, which gets a deferred class registry, and it adds a registration to it. And so this is what's going to ultimately call the Z construct. And so there's two of them. There's the inner register and the outer register. And these are what the call stacks look like if you were to drop breakpoints in the Z construct functions. This is when they get called during engine init. And the outer register is the one that contains a Z construct UClass. And so that's what I focused on here. You can see these outer register functions. And ultimately, that outer register is going to call this function here, which for the first time, there won't be one of these. So it's going to construct the UClass and build us the properties for that UClass. And here's the full call stack for when that happened for my UHT actor class. Again, that goes into the struct UClass, which down here makes a new UClass. And as part of this process, it fills out all that information from the class parameters. And so it's worth noting that at the bottom, when we register things, this is from another file, if you put multiple types in a single file, it sort of registers them all at once. So it populates its enum info, it populates its script struct info, for UStructs, and it populates its class info for UCLASSes, and then it registers them at the bottom here. So these registrations happen kind of like as a group for everything in the file at the end of the file. So now that we've seen how those files work, we can look at what happens when we add things that use like UProperties and UFunctions. So the way I've done this is I've basically took the file and then made changes to it and using a diff to see the changes. So you can see here we've added a myFloat property, and it's a U property, edit anywhere, blueprint rewrite. And this was in the header file. In the CPP file, we didn't really need to change anything, so there's no delta here. There's nothing that changed about the CPP file. And now for the generated files, there actually was no change in the .generated.h file either. So nothing changed in the generated header, but in the .gen.cpp file, or the generated CPP file, there were changes. Now I did modify this a little bit to kind of clean it up, effectively just adding new lines and allowing text wrapping. But you can see the changes here. Since we added this new myFloat property, we now have metadata for it in the category and class. So that like the category gets this class name, module relative path gets that. We have this new static member variable here, new prop myFloat property, and we also get a prop pointers array here. And if we look at where this is defined, it actually defines a lot of data for this property. There's the name, this property flags thing, some more flags here, some offsets, things like that, an address and the z statics. And if we scroll down to our class params, you can see that the prop pointers is populated now, whereas before it was not. And we get an array size, so this array holds all our properties. And the registration is mostly unchanged, just this number changed. So the next question I had was, well, what happens between a raw U property that has no markup and one that has markup? So if we make this change, the generated.h file doesn't change, but the .gen.cpp file does. So we get this category that shows up and the type there. We also get this number to change here. So it went from 0 to 5, and the registration is mostly the same. What was interesting is that 0 to 5 is associated with this eProperties flag. If we find that in the engine, you can see that 5 is 4 and 1. So the 4 is blueprint visible and the 1 is blueprint edit. And so this is likely related to edit anywhere, and blueprint visible is likely related to being blueprint read write. So we can add a blueprint callable U function to this header to explore what changes when we add U functions. To the CPP file, this time we need to give the function a body. And this time the generated.h file, the generated header, does have changes. It has this declare function macro here, which we'll explore in a moment. And it has a new macro here that is injected as part of the generated body. And that macro is just basically calling that declare function. The .gen.cpp file has quite a few changes to it. The first is that there's a ZConstruct type for the function itself, the myBlueprintCallable, in addition to the actor. So it has its own metadata here. It has its own function params. So if we look at the function params being populated for that declaration, it's got the name, it has those eFunction flags, which is similar to the uProperty flags, and various other things here. It has the pattern of the ZConstruct doing a kind of lazy creation. It has a local static for the return function, and if there's not one there, then it constructs a U function, which appears to be a reflected type, similar to UCLASS. And it does that in a similar pattern to construct UCLASS. And then below that, there's this define function, which has some macros right here. And ultimately, it is calling our native function here. So this is, I believe, a hook for the VM machine. We'll explore that a little bit in a moment. And then at the bottom, we have the static register natives function for the actor. So this got populated with a function now. And it takes the function name and it maps it to this exec prefixed version of the function, which is defined right there. And we'll look at that macro in a minute. If I scroll down, we have function info now. So this const expr function array has the name and the ZConstruct function address. If you look at the class params, it populates the func info from right there and sets the array count. So this is going to be provided to that UClass when it gets constructed. If we scroll down, the registration is mostly the same, just some number differences. So I was curious what happens when we go from a raw U function, like used on rep callbacks or dynamic delegate bindings, to one that's blueprint callable, so the blueprint script can call it. The .generated.h file did not change, but the generated CPP file did. And so the main thing that changed was this number here. There's a 4 there and a 0 previously. And this is part of the eFunction flags. The registered info is mostly the same, just different numbers there. And so if we look at what that 4 is, we can see here that 4 is related to this thing here, blueprint callable. And so when we add this, it just puts it in this bit vector there. And so next I want to take a second to look at this define function. So it defines this exec function, and then it has these string of macros. If you look at the define function here, you can read the comment on it, and this is an object macros.h. It is used to define a function in auto-generated boilerplate code. And these are used in this other script macros.h file, which appears to be related to the Kismet VM execution engine. So this define function literally just makes a void function with a object context, some sort of frame thing, and then this result decil. So that's what this is doing here, it's defining the function. And then getProperty appears to create a property for zparam here. So getProperty name, and it just makes a variable type. And the pfinish does some sort of opcode thing. So pNativeBegin starts some sort of scope thing, maybe related to performance capturing. And pN just closes the bracket for that scope. I'm not 100% sure what that is. And then the pthis effectively calls the function that we write. So this seems to be a way to get Blueprint to effectively call our native function. You can see this in the call stacks, and so that's my interpretation of that. It might not be 100% correct, but this exec function is put down here in the funcs array inside of this static register native funcs. It would be also interesting to look at what gets generated for a Blueprint implementable event. So this is a U function that is denoted like that, and this event is only implemented in Blueprint. There's no function body. So all we have to do is add this to our header, and then in the CPP file, we don't change anything because it's Blueprint that will override that event. In the generated header file, we again get some new macros, and these are added to our generated body function here. In the .gen.cpp file, we have some changes. There is this sort of like reflection invocation of the event. So the myBP event, when it's called, it finds the function checked via the name, and it passes along this params struct. The param struct is defined up here in parameter. How it seems to work is it defines a stack variable for that struct, sets a parameter on it, and then it passes that to the event via this process event function. The BP event gets its own static struct with local statics. There appears to be a property in parameter. So what's interesting is this event takes a float in parameter, and that gets treated as its own property to this static struct. So it's as if it has a UPROPERTY, this parameter. There's a prop pointers and function params set up for this. And then we look down here, blueprint statics, we can see where these are defined, and the prop pointers points to that in parameter. There's property flags, just like we saw for UProperties on UCLASSes. Function parameters has a lot of data set here as well. And eventually we have a ZConstruct pattern here for the U function, like we saw for other U functions. And then for the class, we now have function info, which maps our ZConstruct to this name. And in our class params, which builds the UClass, we pass the func info and the size of the array. And then at the end for registration, it's all the same, just some number changes. And another interesting thing to look at is the BlueprintNativeEvent, which is similar to the BlueprintImplementableEvent, except for that we can define a default behavior for it. So this is just a U function that we define as a float parameter, and it's set to be BlueprintNativeEvent. This is all the changes for the header file. Since it has a default implementation, in the CPP file, we have to provide that function body. The .generated.h file, again, does this declare function thing in its own macro, and then that macro is added to the generated body. So we can see there's two macros here, and those two macros are added to the generated body. The .gen.cpp file also changed. Again, we have this kind of param pattern happening where we do process event on a function we find via the name, and the params, which are this here. And the parameter is treated as its own property. Similar thing as what we saw before with the Blueprint implementable event. Eventually we get a ZConstruct pattern where it's building this reflected type for the U function. We have this Blueprint virtual machine hook thing here for a defined function like we saw before. We have this register the name to this exec, and we have some stuff populated in this function info for the actor statics. And then we pass that in our class parameters so that our UClass gets constructed properly. And again, the registration is the same, aside from some number changes. Next, I thought it'd be interesting to look at what gets generated for RPCs, or remote procedure calls, over the network. And we've got three types here. We've got client, which executes on the client machine, server, which executes on the server machine, and net multicast, which basically executes on all the machines. And I have those duplicated to make them unreliable here, and they are reliable up here. So this is all the changes I had to make to the header file. And if we look at the CPP file, these RPCs have a function body that has this underscore implementation. So we have all 6 functions defined down here. Now when it comes to the generated.h file, there is a new macro here, RPC wrappers, which appears to declare all of our virtual functions for us so that they're virtual by default and can be overridden in child classes. There is a declare function for all of these, which is, I believe, setting up hooks for the Blueprint virtual machine. And if we scroll down, these macros are injected into our generated body helper so that these get injected with generated body. And this mostly follows the same pattern we've been seeing for ufunctions. We have this parameter struct here. We have params, set the params, process event after we find a function checked using the params. We have metadata and a ZConstruct struct with member variable statics specifically for the ufunction, in this case the client RPC. The parameters are treated like properties, so it's a full-fledged reflected parameter. We have props pointers for that parameter, which is just a float parameter to that RPC. And eventually we get a ZConstruct for that RPC, which creates a ufunction with reflected data here. We have that virtual machine hook, and that ends the first RPC. And we have sections with basically the same pattern for all of those RPCs. So as far as reliable versus unreliable, here we have a function params flag. If we look at the unreliable one and we find the same thing, function flag, and that is for the client unreliable. If we hop over to here, this is a net multicast reliable. If we look at the function flags and we go to the net multicast unreliable, looking at the function flags, we can see that the unreliable ends in C40 and the reliable ends in CC0. And that's the same thing for these here, the client RPCs, C40 for unreliable and CC0 for reliable. And so it seems that reliable or unreliable is just one of these eFunction flags. So we kind of have the same pattern for all 6 of those RPCs, and eventually we will get to the class. So here we have the static register natives, and we can see that each of these is associated with a underscore exec pattern, like we were seeing in the other BlueprintNativeEvent and BlueprintImplementableEvent. Similar to how we saw before, exec ultimately ends up calling our function here. So all of those are defined for the register natives. And then in the func info, we have all the ZConstructs for these RPCs. And then that func info is passed into the class params, and that array is set. So again, that is ultimately what is used in this construct class here, so that this builds the UCLASS. And the register is also still the same, just different C numbers. Another thing to look at is replicated variables and see how they change the generated files. Here I basically have the same thing twice, one for push replication and one for regular legacy replication. So I have a regular replicated variable, it's just replicated here, say UPROPERTY. And we have another UPROPERTY, which has an onRep callback. You can see my replication videos for details on what all of that means. And then for push replication, we have the same pattern here. We have a replicated one and a replicated using one. And the CPP file, I've had to include some things for push replication. I set up my lifetime replicated properties. So we have the legacy replication there, and we have the push replication there. We have function bodies for the onReps, and we have some functions to mark properties dirty when they're set so that the push replication variables get replicated down to clients. In the generated.h file, there is functions generated for our onReps since they are ufunctions, similar to how we've seen before. There is a function declaration for the get lifetime replicated props. This is why you don't have to actually define that in the header because it populates this for you, though I like to just put that in the header anyways. And there appears to be this netfields private thing that gets defined for the replicated variables. So that is one change from a replicated variable versus a regular property. And it appears to add a validation function for that rep enum. If we scroll down in the generated body helper, we do add that macro that we just saw, which adds those ufunction callbacks. In the .gen.cpp file, we'll see a lot of similar things. The ufunctions callbacks have full-fledged reflection set up for them. So the ZConstruct that builds a function, similar to what we had seen before. And I'll scroll past those for the 2 callbacks. In the static registers funcs, we get those 2 callbacks registered, just like we saw before. In the actor statics, we now have more metadata because this is related to these properties. And we also have basically a variable for each of the replicated variables. So each of these float property params gets set up in this statics. So these are a bunch of declared things. And then below we get these chunks of code for each of those, which set up the property flags, saying it's a float, or this E property flags here that specifies things like we saw before for U properties. So we go all the way down and we can see that the prop pointers is populated with these 4 variables. And in the class parameters, which is used to build the U class, we have funcInfo and prop pointers populated in this thing. And here's that validate function. I don't know that it's worthwhile going through the specifics there, but it has some local statics and just seems to validate some things are correct as far as replication goes. The registration is the same as it has been, just some number changes. So that covers many of the different things you commonly use with a U class. U properties, U functions, replicated properties, things like that. But what we haven't looked at is what happens when we use a UStruct instead of a U class. And so I have a file.h and a file.cpp. In the header file, I just define this UStruct here with some properties, a my float, my actor, my object pointer, and my not replicated float. The CPP file has nothing in it, it's not needed. So if we look and compare this with the actor, or the U class one, we'll see some changes between the U class version and the UStruct version. The first is that all of these constructor helpers are gone. That's not needed for the UStruct. There is a static struct function added that gives us a UScriptStruct. There is this static struct template added. The definition for the current file ID looks a little bit different just because of the different file name. The file.gen.cpp, so the generated CPP, also looks a bit different. We have similar ZConstructs, and now we have one for the scriptstruct myUStruct. And eventually this function here does a lazy evaluation, similar to the ZConstruct, but this is for the outer singleton, and it appears to just be called this. So ultimately it calls getStaticStruct and returns that. So this is probably what's building the reflected type, just like when we build UClass. There are some metadata added for all of the different properties. And for each of those properties, again, we have this like float property params or fObject property params. All these are set up in this statics struct as member statics. This is very similar to the U class, but just slightly different in that the name is different. And this is a UStruct. There's this new struct ops thing, which appears to be some lower level new operators for tstruct ops for this. And then we have all the boilerplate for setting up those properties. And then eventually we have a props pointers, similar to what we saw for UClass. And down here we have struct params down here, which sounds very similar to the class params, which populates various data about the struct. Things like the size of the struct, the alignment, struct flags, metadata, the name, the struct ops function. And we also have a ZConstruct for the struct itself, and this is for the inner, and it's going to construct this UStruct script here, building some reflection data. We scroll down, we see some things missing, but ultimately we see the struct params passed in for this inner struct. The registration is similar, but it's ultimately using struct registration instead of class registration and passing it in slightly differently, which we covered a little bit earlier when we were talking about how this .gen file can register multiple different types all at one at the end. So this is just doing the struct version of that, register struct info. For UENUMs, I have 3 enums here defined in this header. One is a raw enum. It is not exposed to Blueprint, and it's an enum class. The other is also an enum class, but it is exposed to Blueprint. And the last one is an old school enum, like C style, and it's wrapped in a namespace so that this name doesn't leak. So this is the old way of doing it, and I figured maybe there was some difference between these 3 that was interesting. In the CPP file, there's basically nothing other than the include. In the file.generated, we lose all of this like helpers for constructors because it's not needed for enums. The current file ID changed obviously because of a different file name. But what's interesting is there's these for each enum macros that get defined, and it just runs an operation on each of the values, and there's the out. So we get that for all 3 of the enums here. There is some other data here, like this one is a struct trait, it seems, saying that the value is true, that it is a enum class. And for our old school one, I don't see that there, so that is one difference. And then in the file.gen.cpp, we can see there are some different ZConstructs for the enums, similar pattern before. If we scroll down here, we can see there's a function similar to the ZConstruct for the outer singleton. It gets a static enum, and it returns its enum star, so probably building the reflected data there. Only if there is no outer singleton, so otherwise it returns the outer singleton. And there's a template version for getting the static enum. Then there's also a lot of metadata associated with these properties. And we see some mapping of like the first value to this based off the string. This is like the full enum value string, I suppose. And there's some enum params likely used in one of the ZConstructs. So here's the enum params actually getting defined. A lot of reflection data being passed through here. And then we have our ZConstruct, which does the check if there's no inner singleton, and then it constructs the enum, passing in the enum params, same pattern as we've seen before. And then that ends it for the first one. And we basically see the same pattern for the second enum here. And then for the third one, it's a very similar pattern again. We get that construct, metadata, string mapping to values, building the enum params, and a ZConstruct that builds it using enum params. Then at the end, we have our registration, which uses the enum registration compiled in info, which passes in these functions here, which are similar to ZConstructs, they're just not prefixed with it. And we ultimately pass that enum info defined here to be registered with the engine. With UINTERFACEs, we see a similar thing to UCLASSes. So we have the file.h and the file.cpp. In the header, we define this type that inherits from UINTERFACE, and then define this additional type that is actually inherited from by the types. You can see my video on interfaces for that. In the generated.h file, it seems like things got a little mixed up. We still do have like these vtable helpers, they just are up here instead of being at the bottom. And scanning through this, it seems mostly the same. There are some additional things perhaps about it being abstract and an interface in the declare class macro, but it seems mostly the same. There's a generated UInterface body, there's some type tests for class type, this class, etc. And some macros associated with the generated body, a template version of the static class, and then the file ID. And that's it for the generated.h and the file.gen.cpp. Very similar to a UCLASS. The construct actor thing is an engine, but this is related to the core UObject instead of engine. But it still has ZConstructs like we saw before. Very similar patterns to what we've seen before. Metadata, some things like type traits for is abstract, dependent singletons. We have class params because this ultimately is going to use the UCLASS machinery. And a ZConstruct that creates a UCLASS, populates the reflection data. Some constructors defined here, define vtable constructors. So lastly, we have this all defining class info, and it gets registered as class info. And that's it for the generated code covered. And so I just want to call it, remember, this is generated code. I don't think it's important to memorize all that stuff. You know, it can change from engine version to engine version. Since you're not really supposed to be calling that stuff directly, it's all generated boilerplate that may change drastically to implement new features or change the way features work in the engine. And for normal development, you don't really need to explore these files too deeply, and even understanding them isn't really required. You can do a whole lot without really knowing anything internally to those generated files. And I think that's kind of how it was designed, so that you didn't really have to worry about the specifics. You just learned the things to do in the header files and CPP files, which generally is not a lot of work. It's pretty automated. And so you just learn those. You don't really need to understand the generated stuff. But in my opinion, having a high-level understanding of it is helpful. At least it informs you on how to fix some things like linker errors and whatnot. If you know that there's functions being generated and it's failing to link them, it's a pretty trivial fix to set the module to be dependent on the other module. Things like that. So while you're mostly isolated away from these generated files, I think it's just good to be aware of low-level things in C++. So as far as generating those files, you can take a look at these two C# files. They're just in the engine. It's all publicly available from what you download from the Epic Games launcher. And so you can see how it generates those files there. And I wanted to call it that now that you know what reflection is, like, don't overdo it, because reflection can make code really hard to follow. For example, I have an enum here, and I'm reflecting that enum right here, and I'm using like these reflected functions to get like a second value, and then like get an enum by name, get name by index, things like that. And if I find references on second value, it doesn't find this. This is just a string comparison. And so if you go crazy with reflection, it can make the code kind of hard to follow. So I would do it for tools and things like that we talked about earlier. But it's good to know that it's there and it can be used. Just take care to use it when it's actually useful, and don't try to find excuses to use it. Additionally, there's a few extra special files to talk about. I mentioned these earlier. There's the timestamp file, the ProjectClass.h file, and then the ProjectNative.in.gen.cpp file. The timestamp file just seems to be a list of header files that were parsed. At least that's all I can see that it's used for. Not sure how it's actually useful. The ProjectClass.h file is empty in my project, so I'm not really sure what or how this is used. And then this project.init.gen.cpp. This seems to have the ZConstruct for the package for the project. So it does that same ZConstruct pattern that we've seen, and it builds a U package reflected type. There's also some things in here in regards to delegates. But other than that, this file is rather small compared to the other types of files. And that's it. See the comments for corrections, concerns, comments. And I hope that helps kind of demystify some of the more magical part to the engine. So there's still a lot I don't know about this stuff. So again, I don't think you need to memorize the specifics of that, but just having a high-level overview of what you think is going on, understanding of what Unreal Header Tool is doing for you, a mental model. The engine isn't doing magical things, it's using C++, and it's generating the tedious parts for us so that we don't have to write as much code to get those features. So I hope that helps, and until next time.